The 1920 Nobel Prize in Physics went to someone you've probably never heard of, and when I tell you what he won the prize for, you're going to be like, okay, that doesn't matter to me. But he changed the world in ways that really matter, and I can't stress his contributions enough. So bear with me while I try to get this to make sense. But the official wording of his prize was he won for recognition of the services he has rendered to precision measurements in physics by his discovery of anomalies in steel alloys. Whew! Okay, now what that means is with these materials you can make precision instruments that don't change based on what temperature it is outside. It can be 500 degrees, it could be 12 degrees, and you're going to get the same measurement. So these things are very important because what he invented was a material called invar, which is a nickel steel alloy with a near zero coefficient of thermal expansion. I know what you're saying. Hold on a minute, Dr. Imholt. What the heck does that really mean? And how does it really change my life? It really does. Now let's look at why. Now this is the current official 1 meter bar that's held by the US government at NIST. Now this is kind of cool because everybody needs to have the same meter. If I'm building a road, I'm building a bridge, it may involve 5 or 6 different companies, and they all need to agree on exactly what a meter is. We can't have it be 10% off or even 2% off in some cases. It's also important to understand that that meter needs to be exactly the same, whether it's incredibly hot or incredibly cold, because things do change size based on the thermal coefficient of friction. Now, sometimes that can be a small change, sometimes that can be a large change, but when you're dealing with things that go across large distances, that change can add up, and that change can become important. So let's look at a couple of examples of where we allow for that change because these measurements have been taken over the years and are very well known. As you're driving across certain interchanges, especially elevated or bridge building, you will see these little expansion joints. And what those expansion joints do is they're allowing for that thermal coefficient of expansion. That way you don't wind up with funny things happening in your roadway. Well, how bad could it really get, right? I mean, if we just build everything the same, it shouldn't matter. It should all just sort of extend out, right? That's going to happen, right? That's going to be perfectly the way it works. Well, let's take a look. Well, this is what happens if you don't allow for that thermal coefficient of expansion. So this is a couple of railway lines that didn't allow for it. They got cycled through winter and summer heat, and then back to winter and back to summer heat enough so that you wind up with this bend in the railway. Now, there was a time when railways would have to go out and fix that. Since that, engineering has gotten better, alloys have gotten better, and this isn't as big a problem today as it was. But there was a time not that long ago when this was a legitimate problem. Now, how might that impact our lives today? Because sure, I can see the point with railway, I can see the point with a road, I can see the point with a spring in my watch to make sure it times things correctly. All that matters, right? Where else might we care? Well, let's think about that for a second. So not only does his discovery allow us to have a well-defined meter, which of course gives us a well-defined millimeter, centimeter, kilometer, the whole 9 yards, but it also allows us to accurately agree on what the thermal coefficient of expansion is, because now we have a standard meter to measure everything against. That's important when you're building machine tools for certain engines, for certain pieces of industrial equipment. And oh, wait for it, there's one more really important one. If you watched the video on the 1910 Nobel Prize in Physics, you may remember this gentleman by the name of van der Waals. He gave us the gas law relating pressure and temperature. Now, who cares about that, right? Well, if you're on an airplane and you go up in altitude, the pressure goes down. And if the pressure goes down, that's going to have a corresponding shift in the temperature. And sometimes that can be very extreme. So let's think about this for a second. Next time you go up in one of these two gentlemen allowed us to understand what the difference in temperature is going to be at a certain altitude. The other one allowed us to measure exactly what the size of something is going to be and better understand those thermal coefficient of friction of expansions now that we all agree on what a meter is, so that we understand how all these parts are going to change a little bit in size as you go up in altitude, which turns out to be pretty important. So these two gentlemen worked on different projects at different times. I'm not even sure they knew each other. However, without them, we would not be able to fly safely, or build roads that don't buckle, or have railway lines that don't curl, all kinds of things. So before you get on a plane next time, think, hey, physicists out there doing things we may not really care that much about actually enabled that technology to be safe. Engineers built it, based on the scientific principles, which is also shockingly important to get all that correct. But without those principles, what do you build? Everybody, don't forget to click like and subscribe, and we'll see you on the next video.